So I'm going to talk about learning analytics towards better, more equitable learning, and I want to be sure to let you know that there's a big team of folks that have helped with the work I'll talk about, as well as a lot of good sources of funding, including a non-officially announced Schmidt Foundation thing that goes in the blank here, but I'm not supposed to say that yet, so you didn't hear it. The theme of the conference is trustworthy learning analytics, and I think there's lots of ways to think about that, of course, but one way to think about that is that trustworthy learning and analytics produce insights that yield enhanced student learning. And I want to make a contrast with okay analytics, which is better prediction. We do a lot of that. I'll give some statistics from a recent paper that is at least somewhat related to that. But I think we will get more leverage in this field and in the world by pursuing the next two steps here, insight and redesign and close-the-loop experiments. So my talk is basically two stories about that loop, each of which has two parts, an analysis part and a close-the-loop part. So going back to this for a second, another way to say this is better predictions are good, but they're not yet trustworthy because they may not have causal power to improve learning. Just this week, a paper came out in the Journal of Learning Analytics Open Peer Commentary. You can go and comment on this paper. It has this clever but challenging title, A Lack of Direction, Misalignment Between the Goals of Learning Analytics and Its Research Scholarship. You can see a list of authors here, a number of which are here at our conference, so you can talk to them. They did an analysis of LAC papers and found that most papers are not closing the loop or even suggesting a course redesign. Only 11% of the papers they reviewed introduced a change to the learning environment. And they also observed relatively little evaluation of outcomes. Only 29% include any measure of learning. And if a close-the-loop experiment that's going to compare two versions of a course, one with the analytics built in and one without, is going to see whether it helps learning, then it's got to have a learning measure. So got to be smaller even than and there has to be a change too. So that number has to be even smaller than 11. So I don't know, these 89%, they're probably not all better predictions. Maybe 70% is on the high side, but the insight and design stage, we only have about 11%, and the close the loop is probably substantially less than 11%. So just kind of a call out. Let's try to up those numbers going forward. So let me go on to give a couple examples here. So starting first with an analysis of what student choices predict learning outcomes. And this is from a paper in LAC in 2016. We analyzed a massive open online course for psychology, which was part Coursera, which included video lectures, discussion forums, some writing assignments and surveys, and then in each of the 11 units of a course, there was a quiz and a final exam. This was coupled with access for learners to the Open Learning Initiative's Psychology Interactive course that has embedded interactive practice inside of online reading pages. The practice has feedback that targets students' misconceptions and provides them with embedded instruction in the form of hints if they need it. So you all know what video lectures online look like. We call that watching here in the analysis. And then here's an example of in the module on personality as traits. This is a reading activity, so when the students click on this page, we can get a measure that they may be reading it. And then give a couple examples of doing or practice with feedback. So this is an interactive activity on the big 5 personality factors. So 2 of them have been placed here. There's the other 3 that need to be dragged and dropped. And if the student, makes an error, they get a feedback message. If they need help, they can ask for a hint and get a hint. There's other drag and drop activities, like this one's about the brain areas. Of course, there's a number of more familiar multiple choice. There are also a number of what are called submit and compare items in OLI, where you're asked an open-ended question, the student is, and they type, and then they click submit. And the compare part is they see an example of a quality answer from the instructor. So just give you a sense for the different kinds of activities. So we had 1,000 students that completed the final exam in this course, and we analyzed those variables. Basically, the doing is the number of activities they started, the watching is the number of times they clicked the play button, reading is the number of times they went to a page, although we subtracted out the number of page accesses, maybe about 5% that might be attributed simply to trying to get to the activity. It doesn't really change the results at all, whether we subtract that out or not, but little technical detail. There was a pre-test, and of course this total quiz score in the final exam. And what you're looking at right now is the output of a causal inference analysis from an algorithm called tetrad, where we took the table of all these variables for the 1,000 students and a little bit of information about the temporal order of these events. And with that, this is the causal graph that tetrad inferred. And in particular, I want to focus your attention on these weights on the links. These are, all the variables were standardized, so they were in effect sizes, so that each of these links is associated. For example, this one is when a student does 1 standard deviation more of the activities, they do 0.44 standard deviations better in the total quiz score. And then this shows that the total quiz predicts the final exam quite well. And so I don't know, I guess I've always been a fan of active learning, but I was surprised by the extent of these results, which are that the effects, the associations between watching and reading and total and outcomes are positive, but 6 times less than the impact of the online activities. So, of course, this says causal model, but we need to be careful about that, and let me say more about that. But first, let me indicate that this association has been replicated. Here we did it in 3 other courses in another instance of this OLI psych course. This is the ratio of doing the reading. Not all of these had video components. And you can see it ranges from 2 up to 16. This one's because in that statistics course, the readings were not at all associated with quiz outcomes. They're slightly negative, as a matter of fact. The median across these is 6 again, so that's kind of surprising. But we're not the only ones to do it. Later today, at 1 o'clock, there's this paper, The Doer Effect at Scale. I think this is an investigation. Oh yeah, across 7 courses. I didn't have to memorize that. So welcome to go see that. They've been seeing the same thing. One other thing we did in this LAC paper is to try to, there could be a third variable contributing here, like a student who's really likes psychology might be both doing more and learning more. So we wondered, is this effect also within student, not just across students? So if a student does more in a unit, like let's say unit 4, than they do in unit 7, will we see that they learn more, relatively speaking, in unit 4 than unit 7? So we did this mixed effects regression, all 3 of those different kinds of activities, doing, watching, reading, with 3 different counts. The number of activities they did before the target unit, the number of resource accesses, that could be video or reading, the number within, and the number after, right? So we got 9 numbers here in the rows here. So doing, If the outcome we're predicting is Unit 4, then this would be the doing in 1 through 3, and this is in 5 through 11, and this is the doing within 4. And indeed, we get the biggest normalized regression coefficient is for doing within. So it is increasing evidence that active practice causes more learning than passive reading or watching. The reading and watching coefficients, again, are much smaller. In this case, actually, quite a bit smaller than 6 times. But there is still reason for caution here. There could be third variable. Maybe I like the brain unit in particular more so than the personality unit, so I do more there and learn more there. It's also the case, curiously, that some of these after effects are significant, which cannot be causal. There's no way that more doing after Unit 4 makes you better at Unit 4, right? So there is some third variable phenomena. This is all one regression, though, so this indicates that there's a within effect in addition to some possible third variable effect. And maybe there's a third variable effect with the watching, too. All this to say, if we really want to nail this down, we should do an experiment where we prompt students in some way toward more doing and compare it to less. So we've done a few of those, and I'll just describe one of them. But let me just pause for a moment. What you just heard essentially could be summarized as more doing is 6 times more associated with learning than more watching or reading. So now's your time to do active learning step 2. See if you got that. And then there'll be a question about the next phase here. And let me just see if we can get a live update on what's happening here. I'm not sure how good the internet connection. That didn't change too much. We're getting some responses are coming in. Don't copy. And so there's a second question here. I will let you engage in that. Anybody still need the access? If you came in late? There's one there. I'll hold it for a second. Got it? Yeah. So the second part of this, the closed loop part of this story, involves a comparison of active doing versus passive reading. And Paulo Carvalho, who's been a great contributor on a number of these projects, was really the lead on this one. And we turned out this was, again, in a psychology course. We were looking at whether activities without prior reading might improve learning in a classroom. So schematically, you can think of the typical approach as you read, that these lines are text, right? And then you do. And like this might be a description of a psychology experiment, and there are the results, right? So that can be contrasted with essentially similar to what you just did. We just ask, here's the 2 conditions of this experiment. What do you think is going to happen before we even tell them anything else about the psychology? And then show them results. Sometimes there's an explanation here. Why do you think that? But then, so this is predict, observe, and then we say, why do you think that happened? Explain. Then they hear the research-based, the experimenter's explanation, and then they explain it themselves. And so right from the start, there's active learning. There's not a bunch of pages of reading and then practice. So that's the distinction, passive plus practice versus practice and then feedback. And Paulo Carvalho has done actually a number of other experiments like this, but this one's published. The other ones are hopefully going to be out soon. But in this one, he saw, this, by the way, is embedded in a real psych class where the exams were from an experimentalist perspective, maybe a little easy. We wish they were a little harder, but you can see like they do pretty well in the control condition on the exam. But there is a statistically reliable improvement based on this practice plus feedback. In this particular study, we weren't able to really measure learning time, but in some of his other studies that he's been running online, he has just a text condition, upfront reading, just practice with feedback, and then both. And as you can imagine, when you do both, when you ask students to do both, that takes longer. Turns out in those studies, reading's better than nothing, but the practice is better than the reading. And the most surprising results from those is that the practice plus the reading is no better than the practice, but it takes substantially longer. Now, I said reading, but I really meant upfront reading, because they're reading the feedback in the practice, right? It's not like we're holding back information. This isn't discovery learning. This is the instruction, the conveying of information does come on these pages, but it is more responsive to student thinking. There's definitely more experiments that should be run, but there's a strong suggestion from these results so far that maybe we should replace upfront reading with more upfront doing. So link 3, if you want to play along with that. Let's see how we're doing. Refresh here. So we had 74% are now saying 6 times. Yeah, that wasn't hard to keep in memory. Here on this one, upfront practice with feedback combined with follow-up reading would be the next. Actually, any of the 2 here, well, maybe I shouldn't say that while you're still doing it, but yeah. But either the second 2 are essentially consistent with the results we've seen so far. All right, 18 minutes in and on to story 2. We're doing good. So story 2 is an analysis of what student differences account for learning outcomes. And if you like the nitty-gritty of learning analytics, I'll get a little more technical in this phase. But this involves an analysis of 27 data sets that we collected. They're in DataShop, the data repository that has like nearly 4,000 data sets now. If you want to analyze some data, go to DataShop and you can get all kinds of it. Clickstream data of the character that's reflected by these examples. So some are like AI intelligent tutoring systems, like this one for geometry that we built. It was a predecessor of what was licensed to Carnegie Learning. This is an AI tutor for physics, Kurt Van Lane. Students are entering values in this table, and including labels of quantities. Here they're drawing force vectors. This is green because that was judged as correct. They're entering equations. This one's red because it isn't quite correct, so the student got feedback. Here they're having a little dialogue with the intelligent tutor. Pre-ChatGPT, Kurt was building dialogue-based systems. Here's a fraction number line game where there's a battleship there. You got to type in, I don't know, 3/5, right? And then the bomb comes down and may or may not hit the battleship. Derek Lomas did this, put it up on Brain Pop. A day later, 10,000 data points. Pretty impressive in that regard. Building a knowledge component model for this domain was an interesting endeavor. I'll tell you about knowledge component models in a second. Here's the OLI statistics online, which has been demonstrated to double students' efficiencies, another one of these data sets. So, all of them, I hope you see that we're getting this data from students on a step-by-step basis, and it's evaluated by the system to see whether they get it right, essentially on their first try without help. So we're going to use that data to create learning curves. The red is a learning curve from one of these data sets where these are the prior opportunities to learn. So the first time you get a chance to do this, you haven't had any prior practice, so that's 0. That's the intercept value. And then these are averages across all students and all relevant concepts or skills, which we collectively call knowledge components. And we're graphing success here The blue line is the model fit, and I'll go step by step into how the model is built. So where the model is predicting success, that's proportional to this formula that draws on this opportunities as a key component, and then has these other two components, initial knowledge and learning rate. And while these are curves right now, we're going to get to them being lines. So I'm kind of evoking, if you remember your algebra, mx plus b, right? B is the intercept, m is the slope, right? So here's the intercept in this learning curve, 56% on their first opportunity. And then they're going up with each opportunity to practice. But because there's a ceiling here, right, you can't go up at the same amount every time. And that's where, if you know logistic regression, which is the basis for item response theory, you want to bring that in here because we're modeling 0-1 data. And before I get to that, though, let me say that, as I said, the original curve I showed you averages across both students and knowledge components, but we can disaggregate that to create curves for each individual student. And this is an example of what those curves might look like. They certainly aren't that regular, but these might be what the model predictions look like. And one challenge with these is, while it's pretty easy to see, you know, these students started with the same intercept and it was different from those, what about the slope? Like, is this one learning at a faster rate than, it's clearly they are than S2, but what about than S3? It's hard to visualize. And so a nice thing about using this log odds transformation, where you know you can get a real scale here from negative infinity to plus infinity that maps into probability, is that you can essentially straighten out these lines. So, and we can change this proportion now to an equal sign. This is the log odds. The probability of success over the probability of error is the odds, and you take the log of it. That's the basis of logistic regression. And now we can look at how the learning rate here, when we transform the y-axis here to be, instead of in success, in log odds, these lines straighten out. And now the learning rate is constant, and a constant increase at each point. And we can see that this student actually, in log odds terms, is progressing at a faster rate than any of the others. So I set that up because I'm going to show you graphs like that from real data. The one other thing to set up is that I've been mentioning that, you know, these are averaged over the knowledge components, the concepts and skills that students need to bring to bear to get the answers in all those places right. Okay, so how do we build the knowledge component model? So here's a simplified example from arithmetic where we have, this is 3 problems, each of which have 2 steps, and we're coding each step in the problem. So this first step is 2 times 8 is 16, right? Minus 30. The second step is to do the subtraction. One very simple knowledge component model is everything here is arithmetic. That's Q0, right? That's one candidate. But you might say, well, maybe multiplication is different from subtraction, so we should code that separately. So that Q1 is an alternative, where multiplication and subtraction are coded separately. But if you're looking at these, you might start wondering, well, maybe this subtraction's harder than this one because it involves a negative number. And maybe this multiplication is easier than this one because you can go left to right and get it right. But if you go left to right here, right, you get it wrong. So you need to know order of operations to get this one right. So now we can code for those distinctions and we get a more complex knowledge component model. In the extreme, and actually this is true in some of these data sets like on Chinese vocabulary, each task is its own knowledge component, and then you get this identity matrix. But what we've done for all 27 of these data sets is evaluated knowledge component models and then tried to refine them. And basically the idea is which of these 4 options leads to the best predictive fit in the data, and then that's the one we use. So it's the best fitting one to the curve. This is a made-up example. I suspect, though, Q2 is probably the best one amongst these, but I will say that when I've done this with lots of data sets, and I've often been surprised by it. A whole different story. But so how do we put this all together? So we're going to decompose initial knowledge and learning rate into a student component and a knowledge component. Here, and then here's our logistic regression now with that Q matrix mapping item J to knowledge component K. And this parameter is then how hard, it's essentially how easy. The more positive is, the easier that KC is to do at first. So like in geometry area, finding the area of a rectangle is going to have a higher value than finding the area of a trapezoid, because the trapezoid is more complicated. And then on the learning rate side, again, we'll decompose it in a student component and a KC component. And this is essentially how fast something might be learned. So trapezoid might be hard, but students might learn it quickly, or maybe circle area, I'm making this up, takes longer to learn. And I think it's actually one of the things that's slightly surprising in this data is that if you code the formulas as to whether you're applying them to find the area, so forward, versus code the formula, situations where they're using the formula to go backwards, where they're given the area and all but one parameter, that distinction mostly doesn't matter, but it matters for circle area because you have to take the square root, and that's a harder skill, and that turns out to be, this parameter is bigger for that backward circle area than some of the other ones. And then these are the ones we're really focused on in this particular analysis, is where is each student at the start and how fast are they improving. So now we get back to those lines. These are opportunities to learn. For the data sets, we're showing a line per student in this log odds transformed performance measure. And as I'll say later, I was doing this project I wanted to find out who were the fast learners and figure out what self-regulated skills they have. Phil, I'm looking at you because I know you know a lot about self-regulation. So I was really struck though by this, right? Look how parallel these lines are on one hand, and also how different they are in intercept. There's a student here that starts at about 30% correct and another at 88. But the student at 30 is making the same progress as the one at 88. Now they're not perfectly parallel. You can see more variation in this English articles domain. And actually in general we saw somewhat more variation in the language domains than the others. But especially when you compare the learning rate variation to the intercept variation, it's strikingly small. Like there's a lot of intercept, like you might have expected, we actually simulated data like this, that we know students end up with different outcomes, right? Some get an A, some get a C. Why is that? Well, you might expect they all met the prerequisites, so right, they should all have the same intercept, and then the ones who got an A learn faster, right? So it should branch out like this. That's kind of what I was kind of expecting. But we're seeing just the opposite. The ones who get an A are the ones who get an A on your pretest, basically, right? Now, that may sound like bad news for instruction, but I think this is really good news because what it suggests is that every student can learn. It doesn't matter, By the way, there's a few important constraints on these results. They're all in pretty favorable learning conditions where there's a lot of external regulation. They're being given practice problems, they're being given feedback. In less favorable learning conditions, perhaps we would see much bigger learning rate, and I think that's a super interesting question going forward. But in these favorable learning conditions, all students, it appears, can be successful if they're supported, if their motivation and engagement is supported so that they put in sufficient opportunities. Just to show you that, there's some variations. The even columns are the student curves, the odd columns are the KC curves. Like this one has I was talking to somebody about the Matthew effect. This one's the opposite of the Matthew effect in the sense the students starting off lower are gaining more. There's some that look more Matthew effect-like, but I don't know, maybe that one. But again, I hope you see how parallel these are. And I don't have time to go into it, but you might notice that our models can detect differences in slope because they show up on the KC's slope graphs, and some of those lines are even going down, which is, if you want to ask a question about that, that's an interesting and important phenomenon. Just to pop up here, as I said, my original goal was I was hoping to identify high ability learners and understand their characteristics. What we found is highly similar learning rates across students, and this isn't the only time I've been surprised by data. I started my graduate career in computer science doing AI, and then it got caught by maybe we should study people to build AI systems. And the more I collected data, the more I realized how often my intuitions were not right, and the data revealed that the world is a little bit different. So here's a little side message for especially young researchers out there. When you run a study and things don't go as expected, you might be tempted to shelve it, and I've had that temptation sometimes. But it's often, those are the best results because you're really onto something, and as long as your intuition matches others, you're going to be informing people when you come across something unusual. So stick with it. Message of loop 2, student learning rate is astonishingly regular. There's a hopeful equity message that all students can learn from this. So next opportunity for active learning here. See how things are going. Oh, that's interesting. I noticed that at the prior result, most people were anticipating this quite similar learning rate thing. Is that because the paper's been out on archive, or because it's not as counterintuitive to some of you as it was to me? Great, we got responses coming in here. All right. Last close the loop part of the last story. So one way to describe what we were just talking about is that when we see achievement gaps, like socioeconomic status related achievement gaps or racial achievement gaps, there is some scholarship that suggests they arise from opportunity gaps. That it's not that those kids can't learn, it's that they're not getting equitable opportunities to learn. And I like that framing, and I think this data really supports that framing. So the natural intervention then is, how can we figure out ways to give more opportunities? And a related phenomena that we've seen in our AI tutors is that when we graph how much time, how many problems, there's different ways you can do this, in comparison to some outcome measure. This is the number of sections in a math tutor they completed, but this is really highly correlated with like standardized test data, so this is essentially an outcome measure. When we do this kind of graph, we always see these dosage relationships, right? Sorry, skipped ahead here. The more you do math, the more you learn math. The trouble with these things are, the students down here, and there's nothing the AI tutor can do to help the students who aren't using the AI tutor, right? So at the same time, there's been an incredible amount of really great research out of social psychology giving us new insights in the various ways students may be disengaged and not pursuing opportunities because they feel like they don't belong, or they feel like they're not smart in math, or they feel like who's going to use this math anyway, that's utility value. Or they don't feel like they're part of the classroom community, there's not enough relationship building, or that the teacher cares for them. Or they feel like they're expected because they're a female in computer science or an African American in a math class, that to not do well, that's the stereotype threat idea. And all of these have been associated with intervention. So the idea, can we bring these kinds of ideas to bear to move students over to the right, more opportunities, and thus up in this curve. And in particular, in addition to drawing on those research results, the idea has been emergent, like Saga Education, for example, is a strong case of this, that bringing in human tutors into the K-12 classrooms can really add some real benefits. So we wanted to explore this in this personalized learning square project, where the square refers to essentially two different things. The idea of combining AI tutors and human tutors, but also the idea that we want to tutor not only in support of the math learning, but tutor in support of motivation. Part of the leverage here then is that the AI tutor provides data to the tutor around how the student's doing, and in particular can distinguish students who may be they're engaged, but they're not making much progress. They might be wheel spinning, versus students who are not very engaged. So in one case, if I'm Alex, the tutor, I want to focus on motivational interventions with these students and math interventions with these. In addition, we have all these resources that are helping tutors learn about these various social motivational approaches. And if you saw our talk on Wednesday, we also have interactive scenario-based lessons where these tutors can learn these things by doing. So we're applying the same ideas there. We use that predict, observe, explain approach to training tutors. So I'll end here with a description of an experiment we did in collaboration, a quasi-experiment we did in collaboration with the Center for Urban Education that was running an after-school program associated with 3 of our city schools that drew from especially a population of students from low-income neighborhoods and minoritized communities. I'll show you data where the treatment group involved 70 students in this program. 80% were black, 10% Hispanic, 10% white. We're going to blend this human tutoring and technology. And importantly, the tutors here are, they're paraprofessionals. I was about to say they're volunteers, but we did pay them. But part of the training idea is that they're not experienced teachers. So here's the way Ready to Learn worked. Carmen and Cassandra were the supervisors of the whole thing. They had sessions with students that lasted about 2 hours. The first 20 minutes was about relationship building. They had pizza together and talked. The next 80 minutes alternated between tutoring, human tutoring, and online math tutoring, and the groups then swapped in the second 40 minutes, and then they went back to reflection, team building. They also did, in one of these sessions, they did a social justice project. This was in 2020, so their social justice project was around COVID, and students were applying rational number and investigating statistics about COVID in that project. So there's a broader curriculum around the computer tutor use. We had an opportunity to do this quasi-experiment, and randomized experiments are the high bar standard, but I'm a really big believer is when you collect data, you should, because you want to get your early input on whether it works. And there are possible the risks to inference from quasi-experimental evaluation, but I want to show you a couple of things we did to reduce those risks. One thing that can help a lot in these early stages is you can find a way to get assessments from the naturalistic environment. So we got test scores from the school districts, right? Both in the fall and winter before the intervention and in the fall and winter afterwards. Guess why we didn't have them in the spring, right? That's when the pandemic hit. We had some missing data in fall. If you look in the paper, we talk about some imputation techniques. It was 15%, but even there, since we had 2 tests, we combined those measures and it worked pretty well. I mentioned the demographics. So how do we pick the control conditions? So there were about 500, 600 students, middle school students at these same schools who weren't involved, but they weren't demographically matched. So we used this technique, propensity matching, to find a subset. It was 380 of them that were demographically matched. And in propensity matching, there's this nice display that shows for the whole unmatched control sample on various demographic dimensions, how big is the difference between the treatment and the control, right? And you don't want that to be big. So what the black dots show is basically what happens after the selection process, and you want those all to be close to 0, and that's what happened in this selection process with very small exceptions here and there. Here are the results. Nice thing about this NWEA math test is they have this RIT score that works across, that you can pair across grade levels. So the 6th grade test, while it's somewhat easier than the 7th grade test, they have a way of mapping the score on one to the score on the other. So these are those RIT score growth. So 3.6 in the control, 6.8 in the treatment, a near doubling effect. And just for comparison purposes, the unmatched control, as expected, because it's demographically more advantaged, did better. The national average, this is actually a stat outside of the pandemic, is 5.5. So maybe some of this decline is pandemic slide, or maybe this is because the national average includes suburban schools and so forth, right? But in general, you can see these 70 students really progressed in math in a substantial way. That extra opportunities that really helped. One other thing about the quasi-experimental design is if this is a selection effect whereby students who are engaging in this program, enticed to be in it and accepted to be in it, might be generally better students, right? And when, of course, the propensity matching was trying to select for that, like we were matching on their pretest scores. But if they're generally better students, we'd expect them to do better in reading, right? Whereas if the math tutoring worked, there shouldn't be an effect on reading. And this makes logical sense, but if you want to read about this research method technique, it's called a non-equivalent dependent variable test. And indeed what we found is no effect on reading scores. So this helps with the causal inference that it's not about selecting better students, or less likely to be about selecting better students. All right, summarizing. Trustworthy learning analytics produce insights that yield enhanced student learning. I encourage us to do more of this second and third steps here. I gave a couple examples of those. The one I just indicated was a closed-the-loop experiment on hybrid human-AI tutoring that doubles math learning. You can jump in and do this one. I think I'm approaching my 45-minute time limit here, so let me just, you've seen this slide multiple times. I won't repeat the summary. I'll just say thank you, to my collaborators, to my funders, and then take your questions.
Thank you, Ken, for this great talk. We will share mics, I guess, just for logistics. And we have already some questions in Huba, so I invite the audience also to post them there and remind that we have, after the coffee break, an extended session. So there is a question with 4 votes from Adetunji about, so from the experience of these last few days, I think they might be referring to the conference, but also thinking about the studies and all the data that is used. The question mentions, I have noted that the data availability is central to the use of learning analytics. What is your advice for institutions on how to introduce data collection culture that will suit the purpose of learning analytics?
Yeah, that's a super interesting question, that introduce a data collection culture. suggests that it isn't just about building an infrastructure, it's about building a user community. And I totally think that that's super important. I also think it's important to build stuff and start to get it into use. Like my HCI colleagues often talk about user-driven design. My preference is use-driven design. Build it and start getting it into use. And I guess along those lines, user community building, doing educational activities, like workshops with faculty on campus are one way to do that. Like for example, we have these annual week-long Learn Lab summer schools where we use those a lot to build user community.
Thanks, Ken. There is this question from Philip Wen. So it's how tightly linked is active learning on concept A to achievement on concept A? Does active learning on concept A leak to concept B, which was not actively learned?
Yeah, that's a nice question too. The way we've defined knowledge components is it goes the other direction. If there's leakage from A to B, your labels are wrong. It's kind of like germ theory. Right? Germ theory says there's something that explains the disease. We need to find out what it is. If there's leakage from A to B, that means there's transfer. And we need to find the component that explains the transfer. So when we see that in our data, like we might have in that Q1 I showed you, then we see, well, maybe Q2 can explain the transfer. So if you've got such leakage, that's why you don't invent knowledge component models, you discover them. They come from the data.
So there is this other question from Henry Anderson. It says, the relative inconsistency of learning rates on language tasks versus mathematical tasks is a very interesting finding. Do you have any thoughts on what might explain this?
Yeah. By the way, for each of these 4 steps, I linked to associated papers on where those links were. So if you want to get into the details, like we do have a discussion of this question in that paper. And more generally, a discussion of how can it be that students' prior experience puts them at very different places on the intercept, yet, you would think that they vary enough in different prerequisite knowledge that would affect their learning rate. So that's a little bit puzzling. The best I've come to is, and I've seen this in other kinds of analyses like of prerequisite structures, is that what you need to learn isn't just one thing, that the prerequisite structures aren't as linear as we think, that it's often sufficient to be able to, say, learn about fractions visually versus learn about them more symbolically. And as long as you have one of those 2 prerequisites, you can succeed. So getting back to language, in math domains, it's often, there tend to be more pathways. But especially for something as sort of verbatim memory oriented as learning Chinese vocabulary, there's really only one learning process there, memory. And there's no sense making because there are arbitrary associations, and there's no really pattern induction because there are these one-to-one mappings. So my guess is that in the language domains, because there isn't this sort of disjunctive set of paths to learn, there's only one way to learn, that is more sensitive to what might be more fundamental differences in students' say, ability to memorize. I don't have the data, but I suspect, for example, that I'm pretty bad at that sort of thing. Like I have trouble learning English vocabulary. So more research is needed, though, for sure.
There are a couple more questions from Phil Winey, so if I will ask them on your behalf, but if you want to jump in here, are also invited? No, I'll go. Okay. When students read, then do, and don't succeed well enough on achievement, do we have a measure of unproductive, self-regulated learning, or a measure indicating students don't have learning skills?
When they read and don't learn, yeah, well, I mean, you might say that reading is an unfavorable learning condition relative to practice for multiple reasons. One is that you don't have the active learning component, but the other is that you don't have this check on your understanding that you get from active learning, right? And if you know some of the physics education studies, a really nice study at Harvard where they did a crossover design with active versus passive lectures. But they also asked students where they thought they learned more, and they think they learned more from the passive, even though the data shows they learned more from the active. And part of that is during the active questioning, the student who might have in the lecture been going, oh yeah, that makes sense. They get the question wrong, and they realize that they only thought it made sense, but they didn't really get it, right? And so the active learning helps debug misconceptions in a powerful way. So I think, though, that self-regulation, a good active reader, you might know that there's this thing called the cover-up strategy. Like when you're studying your notes or doing a reading, you should cover it up and see if you can retrieve what's there. A good self-regulated learner can make a passive activity into an active one. And indeed, we started to look at this, by the way, in Paulo's studies because we have this reading-only condition, whether the learning rate is higher. The learning rate variation is higher in the reading condition than it is in the practice condition. There is a trend in that direction, but it's a little bit tricky to compare variances like that. But future work needed. Super interesting question, I think.
There is another question here from John Kennedy. Have you applied K-means trajectory analysis to see if there are significant differences in the types of learning growth rates shapes?
I have not applied K-means trajectory analysis, and I would invite you, John, or anybody else to go to DataShop and get these 27 data sets and try K-means trajectory analysis or anything else because there's lots of possibilities that could be tried, and I encourage you to do it.
I'm going to jump into a question from Simon Buckingham. So I'll do it on your behalf, but if you... It says, in the closing Mathia versus human coaching study, did you study the role the human coaches played in combination with Mathia? Could this be a critical role compared to an AI only? Thanks.
Yeah, well, we can only, sort of qualitatively think about what's going on. But certainly the hypothesis is that interaction is critical in two ways. One is there's a back and forth between the opportunity to have human interaction and maybe develop a sense of relationship and belonging as a math student, and then an opportunity to get this kind of, one-on-one deliberate practice tutoring. So that's one reason why we think both are important. The other one is that the data coming from the tutor from the computer tutor can influence what the human tutor does. And I wish we had more detailed tracking data on that. That's certainly one of our goals. I think that's probably a smaller effect than what we saw. I mean, the big effect, in some ways you could say the study's obvious. If you get kids to do more math after school, they're going to learn more. But I will say there's a lot of after-school programs that I've seen, the kids come and they're playing around, but they're not really doing math. So I think part of the power of it is that Carmen and Cassandra created this environment where the kids really do put in time. One little detail is that we looked at the dosage within the treatment on the computer use, and the more they're using the computer tutor in the treatment, the bigger effect that they did. We wanted to do the same thing on the human side, but we only have whether they attended a session or not, and that's just too highly correlated with the tutor data, so that didn't actually work out. But if we're in the future, we're going to try to collect more fine-grained data on both sides so we can get an indication of how much is more human tutoring contributing in comparison to more computer tutoring.